discuss the connectivity and separability. First we can move to the edge connectivity. Okay, so here we consider edge connectivity. Now, each cut set of a connected graph G consists of a certain number of edges. The number of edges in the smallest cut set is defined as the edge connectivity of G. That means a cut set with the fewest number of edges. So, what is meant by the edge connectivity? Edge connectivity means the number of edges in the smallest cut set. Okay. The edge connectivity of a connected graph can be defined as the minimum number of edges whose removal reduces the rank of the graph by 1. The edge connectivity of a tree is always 1. Why? Because in the case of a tree, every edge is a cut set. So, the edge connectivity of a tree is 1. Now, let us consider some example. Consider these figures. Okay, consider these two graphs. We can name this as graph A, B and C. Okay, here we can name the vertices. Here suppose this vertex V4 and here this vertex V. Okay, now here what is the edge connectivity of the first graph A? That means the minimum number of edges is removed, disconnect the graph. So, from the first graph you can see that when we deleting this edge, that graph become disconnected. So, in the case of the first graph, the edge connectivity is 1. Similarly, in the case of the second graph, if you delete any one of the edges, the graph is not disconnected. So, we have to remove at least 2 edges in order to convert the graph a disconnected graph. So, here the edge connectivity is 2. Now, here in this graph, we have to remove 3 edges in order to convert this graph as a disconnected graph. So, here the edge connectivity is 3. Okay, now we can move to the next definition, that is the vertex connectivity. The vertex connectivity of a connected graph G is defined as the minimum number of vertices whose removal from G leaves the remaining graph disconnected. Okay, so the vertex connectivity means the minimum number of vertices whose removal leaves the graph disconnected. Now, what is the vertex connectivity of a tree? In the case of a tree, the vertex connectivity is 1. Vertex connectivity is 1. Now, if we remove any one of the vertex, then the tree become disconnected. Similarly, we can calculate the vertex connectivity of each of these graph Now from the first graph, if we delete this vertex V4, then the graph become disconnected. So the vertex connectivity of the first graph is 1 and that of the second graph is 2. Now if we remove a single vertex, the graph is not disconnected. So we have to remove at least 2 vertices in order to become this graph to be disconnected. Okay. Similarly, if we remove the vertexes V from the third graph, that graph become disconnected. So in the case of the third graph, that means the graph C, the vertex connectivity is 1. Okay. So this is the definition of edge connectivity and vertex connectivity. Now we can move to separable graph. Okay, separable graph. A connected graph is said to be separable if its vertex connectivity is 1. So, if the vertex connectivity is 1, we can say that graph is a separable graph, and otherwise the graph is not a separable. All other connected graphs are non-separable. Okay, if the vertex connectivity of a graph is 1, that is separable graph, and all other graphs are non-separable. A connected graph G is said to be separable if there exists a subgraph G of capital G such that G bar, what is meant by G bar? The complement of G in capital G. G bar and G have only vertex in common. In a separable graph, a vertex whose removal disconnects the graph is called a cut vertex or cut node or articulation point. We already studied what is cut edge. Similarly, here we have a cut vertex. Another name is cut node. Other name is articulation point. So what is meant by the cut vertex? In a separable graph, a vertex whose removal disconnects the graph is called a cut vertex. Now from the above example, in figure C, V is a cut vertex, and in figure A, V4 is a cut vertex. In a tree, every vertex with degree greater than 1 is a cut vertex. Okay, now we can move to theorem. So you may note the statement. Okay, so I will write this statement here. Only the statement, no need to study the proof here. Theorem 4.7. A vertex V in a connected graph G is a cut vertex if and only if there exist vertices X and Y such that every path between X and Y passes through V. Okay, a vertex V in a connected graph G is a cut vertex. So V is a cut vertex if and only if there exist vertices X and Y such that every path between x and y passes through V. So, it is meant by cut vertex. That means we consider a separable graph, and in the case of a separable graph, if we delete the vertex V, the graph become disconnected. So, such vertex is a cut vertex, and a vertex V in a connected graph is a cut vertex if and only if there exist vertices x and y such that every path between x and y passes through V. Now we can consider another theorem. Theorem 4.8. The edge connectivity of a graph capital G cannot exceed the degree of the vertex with the smallest degree in G. The edge connectivity of a graph G cannot exceed the degree of vertex with the smallest degree in G. Okay, proof is simple, so we can consider the proof. Let the vertex Vi be the vertex with the smallest degree in G. Let d of Vi be the degree of Vi. Vertex Vi can be separated from G by removing the d of Vi edges incident on vertex Vi, and hence the edge connectivity of G cannot exceed the degree of vertex with the smallest degree in G. Okay. Now we can move to the next theorem, that is theorem 4.9. The vertex connectivity of any graph G can never exceed the edge connectivity of G. The vertex connectivity can never exceed the edge connectivity of G. That means edge connectivity is the largest one. Okay. So consider the proof also. Let alpha denote the edge connectivity of G. Alpha denote the edge connectivity of G. Therefore, there exists a cut set. Therefore, there exists a cut set S in G with alpha edges. Let S partition the vertices of capital G into subsets V1 and V2. By removing utmost alpha vertices from V1 or V2 on which the edges in S are incident, we can effect the removal of S. That means together with all other edges incident on these vertices from G. Okay, so here alpha denotes the edge connectivity of G. There exists a cut set S in G with alpha edges. Let S partition the vertices of G into subsets V1 and V2 by removing at most alpha vertices from V1. The vertex set V1 or vertex set V2 on which the edges in S are incident. We can effect the removal of S from G. Okay, this completes the proof of this theorem. Now let us move to a corollary also. Consider the corollary. A very cut set in a non-separable graph with more than 2 vertices contains at least 2 edges. Now, next theorem 4.10. The maximum vertex connectivity one can achieve with a graph G of n vertices and E edges where E greater than or equal to n minus 1 is the integral part of the number 2e divided by n. That means integral part of 2e by n. The maximum vertex connectivity one can achieve with a graph G of n vertices and e edges is the integral part of 2e by n. Okay. Next, a graph G is said to be K connected. What is meant by K connectivity? The next definition is K connectivity. A graph G is said to be K connected if the vertex connectivity of J is K. If the vertex connectivity of G is K, we can say the graph is K connected. So, a one connected graph is same as separable graph. Okay, one connected graph means separable graph. Now next, theorem 4.11. A connected graph G is K connected if and only if every pair of vertices in capital G joined by K or more paths that do not intersect and at least one pair of vertices is joined by exactly K non-intersecting paths. A connected graph G is K connected if and only if every pair of vertices in capital G joined by K or more paths do not intersect and at least one pair of vertices is joined by exactly K non-intersecting paths. Now the next theorem. Theorem 4.12. The edge connectivity of a graph G. The edge connectivity of a graph G is K if and only if every pair of vertices in G is joined by K or more edge disjoint paths and at least one pair of vertices is joined by exactly K edge disjoint path. The edge connectivity of a graph G is K if and only if every pair of vertices in capital G is joined by K or more edge disjoint paths and at least one pair of vertices is joined by exactly K edge disjoint paths. Okay, so you note all these theorems. Now need to write the proof. Okay. Next, we can consider one definition too. Here, What is meant by the non-intersecting path or vertex disjoint path? A path with no common vertices except the two terminal vertices are called non-intersecting paths or vertex disjoint paths. Okay. Thank you all.